Hello everyone, this is the first video for the unit Algebra. In this first lesson, we are going to cover the number sets. We are going to talk about rounding and significant figures, in particular for the requirements for your IB problems. Some of the properties of exponents and how to operate them. And finally, scientific notation. So we're going to start by talking about number sets. Let's consider a set right here where we have the numbers that we use to count with. So we count with 0, 1, 2, 3, 4, 5, etc. These numbers are called the natural numbers and they are represented with an n. Then we can make an extension to this set when we consider all the same natural numbers but also with a negative sign. Then that set is called the integers set, and we represent it with the letter set. And it will include the 0, 1, 2, 3, 4, 5, etc. that we had before, but it will also have the -1, the -2, the -3, the -4, etc. This set is larger than the natural set, of course, but it is also included within another set that we are going to call the rational set. Now, all the members of the rational set can be expressed as fractions that are no longer able to be reduced anymore. So, for example, 1 is a fraction in the sense that you can write it as 1 divided by 1. Or 3 is a fraction in the sense that it can be written as 3 over 1. And -4 is a fraction because you can write it as -4 over 1. There are other rational numbers that don't result in integer numbers, and those are the ones that we are adding in this area to complement the set. So we're talking about numbers that look like 1/2, 2/3, -5/7, etc. Now, inside these sets, all of these numbers, again, can be written as fractions. Numbers that cannot be written as fractions, we can categorize them in two ways. One is by the inclusion of all the numbers that have roots that cannot be reduced or calculated landing in an integer result. So, for example, 4 is a rational number. The square root of 4 is 2. That number is already here. But the square root of 2, the square root of 3, the square root of 5, those numbers are not here anymore. So we need to include them. And by doing that, we are going to create another set that is called the real algebraic set. And we are going to represent it with an AR right here. So like we said, the real algebraic set will include numbers that are not in this set already, and will include those numbers that have radicals, like the square root of 2, the square root of 3, the square root of 7, and numbers that are combinations of numbers like this one, like 1 plus the square root of 5 divided by 3. That is also an algebraic real number. And then we can think of all the other numbers that we can't write as a radical or as a linear combination of a radical. And those are all the other numbers that have decimals that are non-repeating. And those numbers are pi, for example, e minus 2 pi, because they can be positive or negative. The same here. This could be -√3. We're including that one there. And then by including these other numbers, now we have created an even bigger set that we are calling the real set of numbers. So the real set of numbers includes every single number that you know. These two sets of numbers are called irrational numbers. And we recognize them because when they are written in decimal form, they are decimals that are non-repeating and never ending. However, the last set that we added, these are called transcendental numbers. So to summarize, we have 5 sets of numbers that are contained into each other. The natural set of number is the smallest one and is contained into the integer set, and the integer set is contained into the rational set, and the rational set is contained into the algebraic real number set, and the algebraic real number set is contained inside real numbers set. Now we are going to extend this set of numbers beyond the real number set in following topics, where we are going to expand this until we have the complex set of numbers. Before we move on to the second point, rounding and significant figures, I just want to show you 2 questions here that belonged to the program called Math Studies. You guys are not going to get questions explicitly on these numbers, but it is important that you are able to recognize where each number falls into, especially recognizing the properties of the numbers. So I'm going to quickly work in one of these questions, and I'm going to leave the other question for you to do and submit by the end of next lesson. You are going to submit it to the Dropbox in ManageBack. So I'm going to do question 1, and question 1 says assign each number below with the number set they belong to, and the options that we have are the natural numbers, integers, rational, and real. The first number 5 is given as an example. So we know that 5 is natural, it's also an integer, and it's also a rational number, and it's also real. So to start, let's look at A. That's number 0. So 0 should be a natural number. It is also an integer. It is also a rational number, and it is also a real number. Then B is minus 1.5. Minus 1.5 is not a natural number. We don't count with it, so it's not natural. It's not an integer because it has a decimal part, but it is a rational number because I can write it as a fraction. So this is going to be rational. And since it belongs to the rational set, it will also belong to the real set. Now the next number, 15/16, that is not natural and not an integer. That fraction is not possible to be reduced any further, so it's definitely a rational number, and hence it's also a real number. Pi/3. Pi, we know, is not natural. We don't use it to count. It's not an integer. It has a decimal part. It's not rational. We can write it as a function. It is irrational, and as such, it is going to be real. So this number belongs to the real numbers. We know it's a transcendental number. Now E, 2√5, we also know that √5 is an irrational number. Irrational numbers are real, so we say it's real. And then the last one is 1.23 times 10 to the power of minus 3. So if you're not familiar with this is a scientific notation, and we are going to address it in this lesson towards the end. 1.23 times 10 to the power of minus 3 is a number that is decimal. The integer part of that decimal is 0, so it's 0.00123. That's a very small number, but it is a decimal. It is finite, so we know that it's definitely not natural, not an integer, but it is rational, and it's going to be a real number. So now that we finished this one, I am leaving as a part of your lesson work to do question 2. Now let's move on to the second point, which is rounding and significant figures. For all of your IB answers, you're going to be asked to write your answer exactly or to 3 significant figures. If you can't write it exactly, please do so. If you cannot, please round to 3 significant figures. Don't round to anything less than 3 significant figures, or you may be penalized in the tests. Also, don't round to more significant figures. There are very specific cases when you can round to the nearest integer, and that is, for example, if you're talking about money, or people. But you need to show, I would highly recommend that you always show your actual exact answer and then give a reason of why you're rounding your answer instead of just giving the rounded answer. So 3 significant figures. What are significant figures? Let's consider a number. So this is the number 1379. This number has 4 significant figures. So the significant figures are those digits that are different from 0. So 1, 3, 7, 9. These are all significant figures. If I want to round this number to 2 significant figures, what I'm saying is that I'm only interested in the value of the first 2, and I don't really need the others. I'm going to take this number and I'm going to round it to the second digit, in this case to the hundreds. So to 2 significant figures, this number would become 1400. And then I'm going to say it's rounded to 2 significant figures by stating that right next to the answer. So this would be the exact answer, and then this would be rounded to 2 significant figures. Usually in IB, they are going to ask you to round to 3 significant figures. So if you wanted to round this number to 3 significant figures, you have to take the first 3 and round to that position. So if you want to 3 significant figures, you're going to say 1, 3, 8, 0. We rounded up the 7 to 8. So the answer would be 1280 rounded to 3 significant figures. Now, this is very easy when you look at numbers that are big like this. So what happens when the number is very small? So let's take a number that starts with 0. So 0.0012735, for example. This number has only 5 significant figures. So these initial zeros have no value. They are not significant. The first significant figure is 1, the second is 2, 7, 3, and 5, like that. So if I wanted to round this to 3 significant figures, I need to start looking at where am I going to round from the first non-zero digit, in this case the 1. So 1, 2, 7, those are my 3 significant figures. And I'm going to round to that position. So what I'm going to get is my number rounded to 3 significant figures should be 0.0012. And then because the next digit is 7 and the next one is 3, 3 is less than 5, I don't round the 7, like that. So this is rounded to 3 significant figures. Now let's move on to the third part, which is properties of exponents. I just want to review a couple of these properties just so that we can use them for scientific notation. And the first property that I want to review is the multiplication of 2 numbers that are written as a power. So what happens to the exponents if they share the same base? So for example, if you have the number 8 to the power of n, and you're multiplying it to 8 to the power of n, then you are going to keep the base and add the n's. So n plus n is 2n. If they are different, 8 to the power of n times 8 to the power of m, then you have to write it explicitly as a sum in the exponent. But the base is the same, so this is the important part. The base, as long as the base is the same, the exponent is, all you have to do is add the exponents and then keep the same base. When you are dividing exponents like this, that's the second property. What if you are dividing them? So let's say a to the power of n divided a to the power of m. You can always write the a to the power of m that is in the denominator and move it up to the numerator, changing the sign of the exponent. So a to the power of n divided a to the power of m is the same as a to the power of n times a to the power of minus m. And if I use what I learned in the first one, that means I get to keep the same base and add the exponents, in this case n plus minus m. So that should be n minus m. So when you have a division of exponentials, as long as they have the same base, all you have to do is keep the base and then subtract the exponents. So in terms of addition, you can only do that if you have the same exponents and the same base. So for example, an expression like a to the power of n plus a to the power of m, there's nothing you can do. That's it. That's where it ends. However, if they are a to the power of n plus a to the power of n, then you can put them together just by treating them as you would any other algebraic variable. So you would say you have 2 a to the power of n. You have 2a to the power of n plus 1 a to the power of n, then that's going to be 3a to the power of n. So the counter in this case, when you're adding, goes to the coefficient next to the exponent, and the exponential expression doesn't change. The base and the exponent remain the same. Only the counter of how many of those you have changes. And the same goes for subtraction. So if you have different exponents, even if you have the same base, that doesn't work. But if you have 6a to the power of n minus 2a to the power of n, then of course you can just put those together as 6 minus 2 is 4, a to the power of n. Now let's move on to scientific notation. Let's consider we have two numbers here, one that is very small and one that is quite large. So scientific notation is going to be the tool that we're going to use to write numbers that are very large and very small. That is more convenient for us. And let's look at how it would work for the small number. We are going to take the decimal point and we're going to move it until after the first non-zero point. So that means we have to move it 1, 2, 3, 4, 5, 6, 7, 8 positions so that our number becomes 3.5. But when we are moving that decimal point, what we're actually doing is we're multiplying by 10 because we're making the number bigger. 3.5 is a lot bigger than the original number. So to account for that change in size, we need to divide by 10 or multiply by a negative power of 10. So it's going to be 10 to the power of how many spaces did we move? So it's going to be minus 8. In the case of the large number, our decimal point is right here. So if we want to write it in scientific notation, we have to move the decimal point to the left. 1, 2, 3, 4, 5, 6, 7 spaces. In this case, what we're doing is we're dividing by 10. So when I write 1.6, I actually divided by 10 7 times. So to account for this difference in size, I need to multiply by 10 to the power of 7. Now, scientific notation is always going to be in this form, a times 10 to the power of b. This number a has a very specific range of values. It's always going to be bigger than 0 and less than 10. And b can take any value that you want. Let's consider now how do we operate the numbers that are when they are written in scientific notation. For addition, if both numbers are written such that they have the same exponent part, so 3.6 times 10 to the power of 10 and 6 times 10 to the power of 10, then we keep the 10 to the power of 10 intact and we just add the numbers regularly. So this would be times 10 to the power of 10, and then we just need to add 6 plus 3.6, so that's 9.6 times 10 to the power of 10. If the number ends up being larger than 10, remember that this number has to be less than 10. So we would move the decimal point one more space to the left, so this would increase to the power of 11. When they are different, it becomes a little bit problematic because then you in principle cannot add them. We talked about it in the previous section, properties of exponents. They have to have the same exponent in order for us to add them. So what you can do is you can rewrite the numbers so that they share the same exponent. So this way, 2 times 10 to the power of minus 3 changes to 0.2 times 10 to the power of minus 2. And now that the powers are the same, we can just add them normally. So this would be 1.2 times 10 to the power of minus 2. Now let's look at subtraction. So subtraction has the same principle as addition. You need to have the exponents to be the same. So if they are different, what you want to do again is to change the numbers into an expression that has the same power of 10, and then you can proceed to subtract them. And finally, remember that if your number is larger than 10, then you have to rearrange this so that this coefficient is always less than 10. Now let's finish looking at multiplication and division of numbers using scientific notation. For this part, it's going to be very important to use the properties of exponents that we discussed before. Basically, what you're going to do is you're going to multiply the coefficients as you would normally, and then operate the exponential parts using the properties. So in this case, for the first example in multiplication, you want to operate 2 times 8, which is 16, and then you want to say times 10 to the power of, because it's a multiplication of exponents with the same base, that would be 5 plus 3. So this is going to be 16 times 10 to the power of 8. And finally we fix it because 16 is bigger than 10, so 1.6 times 10 to the power of 9 would be the final answer. In the case of division, we do the same. First, we are going to operate the coefficients. So 6 divided by 2 is 3. So this is 3 times 10 to the power of. And we know that when we're dividing exponents, we have to subtract the exponents. So minus 7 minus 2. So the answer is 3 times 10 to the power of minus 9. Now I would like to invite you to complete the task that I set for you in the number set section, and please submit it to ManageBack. And I hope to see you in class with all the questions that you have about the video and the reading, and hope to see you ready to do the practice that I have assigned for you in Cognity. So don't forget to bring your login details, and I'll see you next time.